Okay, moving on. So there are different kinds of differential equations. There are the two, well, let's say there's two broad categories. There are ordinary differential equation, or ODEs, as they're oftenly abbreviated. An ODE is simply a differential equation that is about a quantity, and that quantity, let's say y, depends only upon one variable. So here are three examples of different ordinary differential equations, or ODEs. So in all of these, we can think of the dependent variable if we want to. Really, we don't even have to go that far. We can just think of there being two variables that are related to one another. So in this case, y, and then y depends on t. And we could also treat it the other way around. We could think of t dt dy, where t depends on y. Because truly, if one depends on another, they are related in some sense. So there's only two variables here. There's nothing else. You could have a partial differential equation, or a PDE, which are much, much, much harder to solve, but they do show up in lots of areas of physical sciences. Okay, so the order of a differential equation is simply the order or the degree of the highest derivative that appears in the differential equation. So this is a first derivative. So this ODE would be a first order. This would also be a first order since we only have a y prime making an appearance. But over here we've got this d squared y dt squared, which is really just another notation, Leibniz notation, for y double prime, or the second derivative. So this last equation here would be a second order differential equation. Okay, example 3. Show that this y equals ce to the negative t squared is a solution of this. And then, what is the significance of the parameter c? All right, so to solve this differential equation, or so not to solve, we're going to verify. So to show this is a solution of that, we will do so by showing that the left-hand side equals the right-hand side. So the left-hand side is just y prime. So y prime is the derivative of y. So we'll replace in y, so ce to the negative t squared. And let's say here our variable is t, not x, so let's just go back and make this a ddt. So the derivative here would be ce to the negative t squared, chain rule, so negative 2t. Now notice we can regroup things. If I move this negative 2t out front, and then associate the ce to the negative t squared, then you can hear, sorry, my dog is walking away and is very loud on the hardwood floors. This term here, you can see, not hear, that it is y. So this right here is just y, so this reduces to negative 2ty, and that is exactly the right-hand side. So therefore, this implies that y equals ce to the negative t squared is a solution. Now, what's the significance of this value c? Well, notice that our final answer didn't depend, or at the very least our thought process here, our derivation, it didn't actually hinge upon what the specific value of c is. It was let to be arbitrary, and it didn't cause any problems. So all this is saying is it's a way of describing infinitely many different solutions, one for every real value or real number that you pick for c. So in this way, there is an infinite family of solutions. So no matter what value you pick here for c, that will just be one member of that infinitely large family of solutions to this differential equation. For instance, on the next page here, I took this equation here, and then I just picked different values of c. And then we get this family of curves. I've just plotted a few different values here, negative 1.7, negative 0.3, 0, 0.5, 1, 1.5. These are all different solutions to this differential equation. Something that you will explore in far more detail and depth if you take a differential equations course, which many of you will, if not all of you, will take. There is a way of interpreting this as a slope, because really we know that a derivative is really just an instantaneous rate of change. It's the slope of a tangent line. So effectively, you can think of a differential equation, at least a first-order differential equation, as a way of specifying what the slope is at every single point. Not what the value of the function is, but what the slope of the curve is. So if you know the slope everywhere, if you know the curvature everywhere, then what kinds of solutions, what kind of curves could satisfy this? So the differential equation is actually encoded in this picture here. Might not be obvious, but that's what these arrows are. At this point here, for instance, this point has some x value, and it has some y value. Or in this case, maybe a t-axis and a y-axis, whatever. There's a point. And at this point, if you take the t and the y coordinates for this point and plug it into our derivative that was given, our differential equation, what was it? We had a negative 2ty. If you plug this value of t and value of y into this differential equation, we would actually be able to obtain the slope of that line. So for instance, here, this is c equals 1, so this would be, or not c equals 1. I'm going to follow this over and just say that this is, roughly speaking, y equals 1 right there. So I'll make this be the point something equals 1, something comma 1. And then here, if I drop this point down, we're somewhere between negative 2 and negative 1. Let's say this is negative 1.5. So this is t equals negative 1.5 and y equals 1. So that's our t comma y pair. So if we take this information and plug it into our derivative, so what's our derivative evaluated at negative 1.5 comma 1? Well, it's negative 2ty, our differential equation, the right-hand side of it at least, evaluated at this point, negative 1.51, which gives us negative 2, negative 3 halves, right? Negative 3 halves is the same thing as negative 1.5 times our y value of 1. So this gives us a value of 3, and not so coincidentally, the slope of this line is positive, which matches the fact that this value is positive. And we know that a slope of 1 is this diagonal, so that line right here is not parallel, so that means it is steeper in this case. So at the very least, this seems to agree with our differential equation. So only a sample is drawn here. But really, in actuality, at every single point, even if there's no arrow drawn here, it's because I only did a sample, but in actuality, any point you pick, there is an arrow there. So if we just pick a starting point, we can trace a solution curve by following the arrows. So if I start here, I could kind of follow this trajectory and get a solution. So a differential equation is really, at least a first order, a way of specifying what the slope is everywhere, what the rate of change is, but nothing else. Then, if you know a starting location, you can develop the entire solution from that. You'll investigate numerical methods and things like that in other courses, but that's the basic intuition and the geometric interpretation of a differential equation, at least a first order. So initial value problem is where you are given not just a differential equation, but a differential equation together with a starting point. And that's sort of what's going on up here. Our differential equation is what gives us all of the information about these arrows and what the slopes are and what direction they're pointing in. Then if we have a starting point, we can then follow the arrows to come up with a solution curve or a solution to the initial value problem.